Welcome back to Basic Electronics. In this class, we will continue our discussion of clamper circuits. We will consider a circuit which provides a negative level shift. We will then see how a clamper and a peak detector can be combined to make up a voltage doubler circuit. With the help of the concepts we have learnt, we will solve an interesting problem and get further insight into diode circuits. So let us start. Let us look at another clamper circuit. It's quite similar to the previous one, except now the polarity of the diode is reversed and everything else is the same. And first we will consider the ideal diode model with V on equal to 0 volts. Vs of t is still the same, Vm sin omega t, and Vm is 5 volts. So Vs is varying between 5 and minus 5 volts. And note that the polarity of Vc is now plus here and minus here. Once again, we will make a few observations and then relate that to the graphs that we will see. First, when D conducts, the capacitor charges instantaneously. This point is really no different than the previous circuit, and that is because R on is small and therefore R on times C, which is the time constant, is also small. And in this phase, Vd is equal to 0, so therefore Vc plus 0 minus Vs is equal to 0, and therefore we get Vc equal to Vs. Second point, Vc can only increase, since a decrease in Vc would require the diode to conduct in the reverse direction. And this point again is the same as our previous circuit, except the polarity of the capacitor voltage and the polarity of the diode are now reversed. So this point, the second point, means that Vc can go on increasing up to a maximum and then stay constant, and that is what this is. After Vc reaches its maximum value, which turns out to be Vm, it cannot change any further, and we then have Vo of t, which is Vs minus Vc, equal to Vs minus that constant, which is Vm. And this is a negative level shift, so Vs minus Vm, so that's a negative level shift, and that is where this circuit is different than the previous one. Okay, let us now look at the plots. Now in the beginning, our capacitor voltage is 0 and Vs starts increasing over there, and since Vs comes across the diode and that is a positive bias, the diode starts conducting and therefore the capacitor starts charging. And as we have seen, the capacitor starts instantaneously, so Vc becomes equal to Vs. So Vc, which is the green line, and Vs, which is the blue line, coincide here, and the red one is the output voltage, and because the diode is conducting in this phase, it has 0 volts across it, and therefore the output voltage is 0. And at this point, Vc has already reached its maximum, and that is Vm, which is equal to 5. So subsequently, Vc is going to stay at that value, like that. And then we have this equation to describe Vo of t, which is Vs minus Vm. So if this is Vs, our Vo is simply a level shifted version of Vs. And note that the shift is now downward. Here is the same circuit as the last slide, except we now have a V on of 0.7 volts. And let us quickly go through the results in this case. In the last circuit, VC reached a maximum of 5 volts and stayed there. In this case, it does not quite do that. It goes up to 4.3 volts and stays constant. And let us go through the observations that we went through earlier and relate those to the graphs. When D conducts, the capacitor charges instantaneously, once again, since the time constant is small, as in the last circuit. And in this phase, we have Vc plus V on minus Vs, Vc plus Vd, which is V on, since the diode is conducting, minus Vs equal to 0, and that gives us Vc equal to Vs minus V on. Second point, Vc can only increase because a decrease would call for the diode to conduct in the reverse direction, which is not possible. Third point, after Vc reaches its maximum value, and what is the maximum value now? What is the maximum value of Vs? That is equal to Vm, which is 5 volts. So the maximum value of Vc is Vm minus V on, which is 5 minus 0.7, which is 4.3. After Vc reaches its maximum value, it cannot change anymore for the same reasons we discussed earlier. And we then have Vo of t is equal to Vs of t minus Vc, Vs minus Vc, which is Vs minus Vm plus V on. So it turns out to be Vs minus 4.3 volts. Earlier this was minus 5 volts and now it is minus 4.3 volts. So that's really the only difference, and in this case the output voltage gets clamped to 0.7 volts. That value there is 0.7 volts, and earlier, if you remember, it was 0 volts. So not much difference really, except for the small changes because of V on. We have seen how a clamper works. We have also seen how a peak detector works. We can put these together to make a voltage doubler circuit, also called the peak-to-peak detector. So this figure shows the basic idea behind this combination. The input voltage is a sinusoid from minus Vm to plus Vm, as shown here. The output of the positive clamper, that is this circuit, which provides a positive level shift, is from 0 to 2 Vm, and it's otherwise identical to the input voltage. So the input voltage just gets a shift and it now goes from 0 volts to 2 Vm. And now the peak detector detects the peak of this voltage. And what is the peak of this voltage? This is 0, this is 2 Vm. So the peak of this waveform is 2 Vm. So the output of the peak detector is then expected to be a DC voltage of 2 Vm. So in other words, from a sinusoid going from minus Vm to Vm, we have generated a DC voltage which is double the amplitude, so 2 times Vm, and that's why this circuit is called, this combination is called a voltage doubler. Here is an implementation of the voltage doubler. This first part, consisting of C1 and D1, is a positive clamper. It provides a positive shift, and we have seen this earlier. The second part, consisting of D2 and C2, is a peak detector, and we have also looked at this circuit earlier. And now let's look at the waveforms Vi, V1 and Vo to see how this circuit works. Here are the waveforms for the case where V on for the diodes is 0 volts. That is, we have ideal diodes. The blue curve is the input voltage. The green curve is V1. That's also color coded, so that's blue, that's green, and the output voltage is in the pink color. And as we have seen before, V1 is just a level shifted version of Vi, and it's clamped at 0 volts. So it goes from 0 to 2 Vm if the input goes from minus Vm to plus Vm. The peak detector simply detects the peak of this waveform, the green waveform, which is V1, and the peak is this level here, and that is 2 times Vm, or 2 times 10 in this example, which is 20 volts. It is interesting to note that it takes a few cycles for the output voltage to build up to the steady state. In practice, of course, we are only interested in this part, and we really don't care about what happens in the beginning. But if you're curious, it's a good idea to plot the diode currents and the capacitor voltages and try to figure out why it is taking so many cycles to reach the steady state. The circuit file for this example is available, and you are encouraged to run the simulations. Okay, now let us look at the case where V on is 0.7 volts. And as we have seen before, the positive clamper now clamps V1 at minus 0.7 volts rather than 0 volts in the earlier case. And therefore, V1 does not go to 2 Vm, but it goes to 2 Vm minus 0.7 volts. Also, the peak detector does not detect the peak of V1, but its output is the peak of V1 minus 0.7. So we have two diode voltage drops involved, and therefore the output, the pink line here, is 2 Vm, which is 20 volts, minus 1.4 volts. And that is a circuit file available to you to run this simulation and look at the various waveforms. Let us now consider this circuit with two diodes. It is somewhat similar to the clamper circuit that we have seen earlier. The difference is, in those circuits we had only one diode. Here we have two diodes. So in the clamper circuit, the capacitor voltage could only increase because there was no path for the capacitor to discharge. This situation is different. We have a charging path for the capacitor through this D1, and there is also a discharging path for the capacitor through D2, like that. Okay, let us look at the problem statement now. Here is the input waveform going from minus Vm to plus Vm. This could be, say, minus 10 volts to plus 10 volts. The high interval, that means the interval in which the voltage is high, is marked as T1 over here, and the low interval is marked as T2. And the IV relationship for the diode is given over here. So when the diode conducts, it has a voltage drop of 0.7 volts, and for any voltage less than 0.7 volts, it does not conduct. The current is 0. Here is the problem statement. Assuming R1C and R2C to be large compared to T, find VO of T in steady state. VO is the output voltage here. What are these quantities, R1C and R2C? Let us look at this circuit. The charging path is like that. So we see that the charging time constant is the product of R1 and C. So R1C is the charging time constant. What about discharging? The discharging path is like that, and therefore R2 times C is the discharging time constant. This problem does appear to be somewhat complicated, but we have two simplifying factors. One, we are dealing with steady state, that means periodic steady state, and second, these time constants are given to be large compared to T, and that means that they are large compared to T1 and T2 as well. And this will have implications for our analysis, as we will see. Let us now make a few observations about this circuit and then write equations and figure out what VO of t should be. Charging time constant tau1 equal to R1C, as we have already seen. Discharging time constant tau2 is R2 times C. And since tau1 and tau2 are both much greater than t, the period of the input waveform, we expect Vc to be nearly constant in steady state. And why is that? What is the meaning of tau1 much larger than t? So that means if the capacitor is charging, for example, that charging process is going to be very slow. So that means in this time the capacitor voltage will hardly change. It's going to charge so slowly that we will not even notice the difference in this interval. Similarly, if the capacitor is discharging, we will not really notice any difference in one interval like T2 because it will discharge so slowly over several cycles. So because of that, we can say that the capacitor voltage in steady state can be treated as a constant, and let us denote that constant by Vc with a superscript 0. And now we can get back to VO of t. What is VO of t? It's Vi minus Vc. So VO of t is Vi of t minus Vc of t, and the huge simplification that is made possible by this assumption is that the capacitor voltage is a constant. So therefore our steady state output voltage is simply the input voltage minus this constant Vc with a superscript 0, the steady state value of the capacitor voltage. So let's look at an example and verify that these actually happen, and then we will derive an expression for VO of t in steady state. Here is an example. The input voltage is going from minus 10 to plus 10. That means our Vm is 10 volts. T1, the interval of high input voltage, is given to be 0.25 milliseconds, and T2, the interval of low input voltage, is given as 0.75 milliseconds. The other component values are R1 equal to 5K, R2 equal to 10K. The turn on voltage of the diode is 0.7 volts, and the capacitance is 10 microfarads. Now let us check whether the condition given in the problem statement, that is R1C and R2C being very large compared to T1 and T2, is valid or not. What is R1 times C? 5K times 10 microfarads. So that is 50 milliseconds, and 50 milliseconds is surely large compared to any of these numbers. What about R2 times C? 10K times 10 micro, so that means 100 milliseconds, and that too is large compared to T1 and T2. So the condition stated in our problem is indeed valid. About the capacitor voltage, we said that we expect Vc to be approximately constant, and that is observed over here. And what is that value? This is 0 volts, this is minus 5, so Vc is about minus 2 volts. Now to proceed further, let us look at Vc in an expanded form. Here is the capacitor voltage as a function of time, and we see that it is nearly constant but not exactly constant. It varies between about minus 1.9 volts to minus 1.84 volts, and during this interval, when the input voltage is high, the capacitor voltage rises, and that corresponds to charging of the capacitor through D1. During this interval in which the input voltage is low, the capacitor voltage decreases, and that corresponds to discharging of the capacitor through D2. And note that our capacitor voltage waveform is periodic. This value is the same as the VC value after one period, that is this one, and that is the meaning of periodic steady state. Alright, let us now look at the capacitor current. That is what it looks like, and notice that it is consistent with our comments so far about the charging and discharging of the capacitor. During this interval, when the capacitor is charging, IC is positive, and during this interval, when the capacitor is discharging, IC is negative. Let us try to understand why there is a charging phase and a discharging phase in the first place. So let's consider this situation in which Vi is constant, equal to plus Vm. So we don't have these changes, we just have a constant Vm as the input voltage, just a DC voltage. And what do you expect to happen? Initially there will be a capacitor current, but as t tends to infinity, as we approach the steady state, all voltages will become constant, so therefore Vc will become constant. C dVc dt, which is IC, will become 0, and the capacitor will look like an open circuit. There would not be any voltage drop over there, and the entire input voltage Vm would then appear across the capacitor. So this end of the capacitor would be at Vm, and this other end of the capacitor would be at 0. So in other words, Vc would have become equal to Vm. So that is exactly what is happening in the charging phase. So the capacitor voltage is trying to go all the way up to plus Vm in this phase. Of course, it does not quite happen because we then have this transition of the input voltage, and so therefore the discharging starts. Okay, now we want to find the value of Vc approximately, assuming it's nearly a constant, and for that purpose we will use charge conservation. We have come across this concept also when we discussed RC circuits, and it has to do with periodic steady state, and what the situation we have here is periodic steady state. Everything is periodic: Vc, Ic, Vi, Vo. In particular, the charge on the capacitor is also periodic, and we are going to use that to figure out what Vc should be. So what is the change in the charge on the capacitor in one period? It is 0 to t Ic dt. That is because Ic is dq dt, and this we can split into two parts: integral over 0 to t1, this phase, and integral from t1 to t1 plus t2, that is this phase. And these two together should add up to 0, because we don't expect any change in the capacitor charge between 0 and t equal to capital T. And we can see in this figure that it is actually happening. This area, which is the first integral, is positive because this is over 0, and the second integral is this area, and that is negative. And it turns out that they are equal in magnitude and opposite in sign, so they add up to 0. Okay, so next, what is IC in this interval? It is Vm minus Vc this is plus Vm minus Vc and minus V on, the voltage drop across R1, and that divided by R1. That is our IC. That is because the charging path is like that, and that is a constant, nearly a constant, because Vc is nearly a constant. Now, so therefore the integral is simply that constant multiplied by T1. So that is what this term says. What about IC in the discharging phase, that current? Let us find the voltage drop across R2 in the discharging phase, and that will give us the current that we are looking for. So let us see what this node voltage is first. This is minus Vm when the capacitor is discharging. So minus Vm minus Vc. So this node is at minus Vm minus Vc. So the voltage drop between these two nodes is 0 minus Vm minus Vc. That is this entire voltage drop here. And from that we need to subtract the voltage drop across the diode D2, which is V on. So that is what we have done over here. So that gives us the voltage drop across R2, and that divided by R2 will give us the current. Now it's a simple matter of solving this equation for Vc. Let's take Vc on one side, and we get T1 by R1 plus T2 by R2 times Vc here, and everything else on the other side, and that gives us the value of Vc. And for this example, with the numbers given here, Vc turns out to be minus 1.86 volts, and of course it agrees well with our simulation results. Once we know Vc, we know Vo as well, because Vo is simply Vi minus Vc. So Vo is going to be Vi minus 1.86 volts, so Vi plus 1.86 volts. So that is a positive shift of Vi. So this is our Vi, the light blue curve, and Vo is the same as Vi except for a positive shift of 1.86 volts. In summary, we have seen how a voltage doubler works. We have also considered an interesting diode circuit which could be analyzed using the concepts involved in the clamper and peak detector circuits. In the next class, we will see how diodes can be used in rectification, that is, conversion of an AC voltage to a DC voltage. Until then, goodbye.